Okay, good afternoon, everyone. So we will continue our study on root systems. So we will prove one proposition 8.42. So we have a root system. If mu is dominant, then W mu is less than or equal to mu for all Weil group W. So dominant means is in the closure of the fundamental Weil chamber, or in other words, if you take the inner product with any simple root, then it's non-negative. So if this is dominant, then we define this partial order on root systems. So if you apply Weil group element, it will only get smaller or lower. So proof. So first we claim this. Claim mu is the unique maximal element of VW. No, W mu. So this is a set of elements of this form for a Weil group element W. But because Weil group is finite, this is finite set. Okay. So whenever we have a finite set and we have poset structure or partially ordered, this is a partially ordered set. We have partial order. Whenever we have a finite set with a partial order, then there is at least one maximal element. Maximal means it is not lower than any other. Okay. So proof of the claim. So we can find a maximal element. So let lambda be any maximal element. Because it's finite, we can always find the maximal element. There could be many, at least one. And let's consider any simple root. And we want to show that first of all, if this is a maximal element, then we cannot have this. So if lambda inner product with alpha is smaller than 0, then what is S alpha applied to alpha lambda? This is 1 minus 2 times alpha lambda alpha, right? This is the definition. And this is if this is smaller, that means this constant here, this is positive. Or strictly positive. This is strictly positive, right? So lambda plus something positive alpha. Then this, by definition, is greater than or equal to, it's strictly greater than because it's not equal, right? Because we add some positive number times simple root. But then this is a contradiction to the assumption that lambda is a maximal element. So this is impossible. It's contradiction. This is contradiction to the assumption that this is maximal. Okay? Maximal by definition means we don't have such an element, right? And by the way, of course, this is inside W mu, right? Because lambda was in W mu, so lambda is W times mu, and then S alpha is another element in W, so it's still inside. So that's why it's a contradiction to the assumption that lambda is a maximal element of W mu. All right? So it's a proof So this is impossible, so therefore we must have a non-negative inner product for all alpha. What does that mean? Lambda is dominant, right? So any maximal element in W dot mu must be a dominant element, okay? But now we recall that proposition 8.29, we've seen that W applied to mu. So this is the orbit of the root mu. If you intersect this with the closure of the fundamental domain, of our fundamental Weyl chamber, there is only one element here. We've seen this. Therefore, mu is, we know that mu is a dominant element. So, but recall, this dominant means mu is in the closure of the fundamental Weyl chamber, right? Mu is the only dominant element in here, because mu is in here, of course, and it is also here, but that's the only element. And we assume that lambda is maximal, and then if it's maximal, it's dominant, that means lambda must be mu. So that's the proof of the claim. So any maximal element must be mu. That means mu is the only maximal element. In particular, there's a unique maximal element. So that's the proof of the claim, but we still have to prove this proposition. Okay, let me move on to the next page. So we want to show, so what is the statement? We want to show that lambda mu is less than or equal to mu. But this means mu is the maximum element. So I told you there's a difference between maximal and maximum. Okay, maximum means it is greater than everything else. Maximal means it is not smaller than anything else. It's not quite the same thing. Okay, so in fact, we want to show that mu is the maximum in mu dot in this set, i.e., that means mu is higher than everything in this set. This is what I mean by the maximum. Okay. So how can we show this? So to do that, let's define this set X to be the set of all elements here that is smaller than mu, lower than mu. Okay. But of course, this is a subset of mu in the orbit of mu. So if you want to show that mu is the maximum, what do we need to show? We need to show that X is in fact the whole set. If X is the whole set, that means mu is the maximum. Okay? So we need to show that X is indeed the whole set. Okay? How can we do that? So for contradiction, suppose it's not the case. X is not equal to this. Then we can find, say, nu inside this that is not in X. Okay? So we have a diagram like this whole thing. This is X, and there is some element here. Okay? And we will find the contradiction. So claim nu is a maximal Oh, sorry. I need to say something. We can find element there, but in particular, we can find a maximal element in this. Because this is a finite set, finite non-empty set, we can find the maximal element there. So it is maximal outside X. That is not smaller than anything else in this set. Okay? We can take on a maximal element, not just any element, but maximal element. Then the claim is, this is maximal element not only in this, but it's also a maximal element in the whole set, mu W, W mu. But if the claim is true, if you can prove the claim, then nu must be equal to mu, because mu is the only maximal element in the whole set. But that will be a contradiction, because mu will be in X then. So we will prove this claim. So suppose not for a contradiction. That means then there exists, if it's not maximal, there is an element in here such that nu is smaller than lambda. Okay? If it's not maximal, there must be an element like that, because otherwise we call it a maximal element. But this, what is this lambda? Lambda must be in X. Is that right? Why? Because if lambda is not in X, that means lambda is in here, and lambda is greater than or equal to nu. It's a contradiction to the assumption, to the fact that nu is maximal in here, right? So this lambda must be inside here, because everything here must be, it cannot be bigger than nu. That's the definition of the maximality. So lambda is here, but now what does that mean? Then, by definition of X, lambda, so nu is smaller than lambda because of this, but lambda is smaller than, where is it? Lambda is smaller than mu because lambda is in X. That means nu is smaller than mu, but then this implies nu is in X, which is a contradiction. That means it has to be the case. Yeah, this argument is a little slightly complicated, but yeah, it's kind of a technique used in when you are dealing with partial ordering. So by the claim is proved by the claim. Nu must be equal to mu, because mu is the only maximal element, but then this is inside, of course, X is a contradiction. So this cannot be the case. We must have X must be equal to mu, and that's the end of the proof, because we got a contradiction if we suppose this. Okay? All right. And then the next proposition. So if mu is strictly dominant and integral, then mu is higher than delta. So what is delta? Delta is the half the sum of positive roots. So proof is actually quite simple. For all alpha, alpha must be a simple root. This is strictly dominant means this must be positive, right? And integral means 2 times mu alpha, so integer. So integer. But it's an integer, but it's strictly positive. That means it must be greater than or equal to 1, because the smallest integer greater than 0 is 1. So by integral. Integral implies this. This is strictly positive implies this. Together of this implies this. All right? So now let's consider 2 times mu minus delta. This is now 2 times mu alpha by the linearity. But we've shown that this is in fact 1. This part is 1. Then this is greater than or equal to 1. So it is greater than or equal to 0. So mu minus alpha, this is dominant. But we show that dominant element is greater than or equal to 0. Mu minus this is greater than or equal to 0, but then of course this is greater than or equal to delta. And that's the proof. So pretty simple. Okay, and let me prove one more proposition. Oh, by the way, I'm not going to prove this because it's quite long. So first, there's a nice criterion for comparing the two dominant elements. So suppose that these are dominant elements, then lambda is in the convex hull of this if and only if lambda is less than or equal to mu. So the convex hull means the smallest convex set containing this set. And the second, for any elements in the vector space, and suppose that mu is dominant, then lambda is in the convex hull if and only if this is less than or equal to mu for all Phi group elements W. Yeah, I'm going to show you an figure of this in a moment, but before doing that, let's give you some note. So if mu lambda, let's consider the first case. If these are dominant, then this is in fact lambda less than or equal to mu. This is if and only if condition. Convex hull of mu, the orbit of the convex hull of the orbit of mu under the Phi group action is contained in the convex hull of the orbit of lambda under the phi group action. Why? Why is that? Let's see. This part is lambda is in convex hull of V lambda, for sure, right? Because lambda is one of the elements here. So lambda is in convex hull of, I think this should be, sorry about that. Oh no, I think that's right. Okay. Okay, let me write and then see. Oh no, this is not correct. Yeah, for me, I usually write lambda is greater than or equal to mu, but in the textbook it's written this way, so I get confused. Okay. But anyway, so yeah, this is equivalent, because for one direction, if lambda is in here for sure, because lambda is one of the elements, then this is inside here, right? Okay. So by 1, if these are dominant, lambda is here, then this is done, right? And the other direction, suppose that lambda is in the convex hull of this, like that. By the way, this implies what? This. By 1, maybe I should write by 1 again. We have lambda inside convex hull of this. But then let's apply W lambda. This is W convex hull of this, right? But in fact, this is invariant under this action because everything is already here. So you can, this is really the same as this. So for every W, phi group element, if you apply lambda, W to lambda, it is still inside this convex hull. That's exactly what this is saying. Okay, that's because every element here is inside the convex hull. So for dominant, it's really if you can compare the convex hull of the phi group orbit, then you can tell whether one thing is higher than the other. Okay, let me show you an example. So here we have type B2 root system. So we have mu. So this, I picked lambda 1 and lambda 2 for the simple root. So delta is like this. And these two rays, they enclose this fundamental Weyl chamber. Right? So dominant elements are inside here. Okay, so mu is a fundamental, it's inside the fundamental group, so that means it is a dominant element. And consider mu2. Oh, by the way, these gray areas, they are the elements lower than mu. They are the elements lower than mu. And let's see mu1. The convex hull of mu1, a Weyl group element applied to mu1, then we can go from here to there and then like that, so we get octagon like that. And this octagon, this is contained in the octagon that is the convex hull of the Weyl group orbit of mu. So the Weyl group orbit of mu is the convex hull So there are these 8 elements, 1, 2, 3, 4, 5, 6, 7, 8. And the convexor is like this thick octagon. And lambda 1 is smaller than mu because if you consider the Weyl group orbit and the convexor of that is inside of this octagon. But on the other hand, this one, if you want to compare this partial ordering between these two, you consider the Weyl group orbit, and it is not really contained in this. So lambda 2 is not not lower than mu. That's what the theorem is saying. Okay? All right. So the proof is a little long, so I will skip the proof. So instead, we will move on to the next section. (8.9) examples in rank 3. So recall that for rank 2, we classified all root systems. A1, so rank 2, so recall rank 1, just A1, right? Dimension 1, only we have one root system. Rank 2, we have like A1 times, or let's write direct sum, or B2, A2, B2, G2. There are 4 possibilities. What about rank 3? So now we want to see all root systems of rank 3. So if so let this be a rank 3 root system, and so suppose for the simpler case that R is reducible. What does that mean? That means we can decompose this into 2 non-trivial root systems, and because the degrees add up, the degree of this must be, or rank must be 1. One of them has rank 1, the other has rank 2. We can always decompose like that, but there's only one root system of rank 1, so in fact this is A1 plus something R2, where R2 is what? One of them. R2 is one of them. So we know exactly what R should be. So it's simple. Now we need to consider irreducible root systems of rank 3. So root system rank 3. Now you consider, if, by the way, if R is irreducible, then I'm just telling you the fact. Without proof, there are only 3 possibilities: A3, B3, C3. And these are, in fact, root systems of Lie algebras SL4C, SO7C, and SP3C. Okay, so each respectively, and we will look at each of these irreducible root system. So first, root system A3. So we can write down explicitly what this is. This plus minus 1, plus minus 1, 0, 0, 0 plus minus 1, 0 plus or minus 1 plus or minus 1, like that. So there are four vectors here. So 4 times 3, so there are 12 roots here. And these are in fact the 12 vectors pointing at the midpoint. There is a nice way to visualize this of a unit cube centered at the origin from its center. Okay, so as you can see, I brought several models. So actually, this is type A3 root system. Just green, we have green edges or green vectors coming from the origin. And as you can see, we have this, what's that, cube. The blue edges, they form a cube. And then you can see this, every green edge is from the origin to the midpoint of each side. So it's a type A3 root system. It can be easily visualized very nicely like this. And the delta here, we can pick delta in this way, 1 comma minus 1. There are, of course, several different ways, but this is one possibility. And in Weil group, we know that the Weil group of AN is a permutation group on n plus 1 elements. In this case, it's the permutation group on 4 elements. And in fact, it has geometric description in this way. Symmetry group of the tetrahedron, regular tetrahedron. It's not clearly visible from here, but there is another way to understand the type A root system. This looks a little complicated, but you know, this we have 12 vectors. Look at their endpoints. We have 12 endpoints, and consider the convex hull of them. Convex hull of these 12 midpoints, then we get this polyhedron. I think it's called cube octahedron. So we have center, but now instead of pointing midpoint, it points to every vertex of this outside polyhedron. And you can see this little triangle or tetrahedron sitting inside. And in fact, if you reflect, say for instance, we have this vertical vector. So what is the Weil group S element S? Let's say this is alpha. The S alpha means reflect about this plane. Then you can see the tetrahedron, it stays the same, except we just reflect these two. So it's like a reflecting about this. So that these 2 points, they stay as they are, but these points get sent to this, and this point gets sent to this. So it really preserves this tetrahedron. And you can check, because we can, for any 2 adjacent vertices of a tetrahedron, we can always reflect them. That means we can have a complete symmetry of the tetrahedron. And if you count the number of elements, there are 24 elements, right? 4 factorial is 24, and that's exactly the symmetry group, the same as the order of the symmetry group of this. So that's why it's the isomorphic to the symmetry group of the tetrahedron. Okay. Oh, by the way, so you can think of these 4 elements as like vertices, 4 vertices of tetrahedron. Because we've seen that for any 2 vertices, we can reflect them. Oh, yeah. And type Bn, root system type Bn. B3. And of course, we are still in the three-dimensional space, and the set of roots is the same. We have the roots in type A3, but we add these 6 more vectors, plus minus 1, 0, 0, 0 plus minus 1, 0, 0 plus or minus 1. Okay, what is that? So we start with this. Just imagine that this is, say, x-axis, this is y-axis, and this is z-axis, right? You can see x, y, and z. And this means that 6 vectors, they are exactly the unit vectors lying on one of the axes. So we have to add one vector pointing to the face. So basically we add one vector pointing to the center of each face. So 6 more vectors. And that's exactly this type B3 root system. So we still have the 12 green vectors, but now we have 6 more blue vectors, so type B3. And we can write down explicitly the base elements, but you can see these vectors with this white point, they are the 3 root base elements. Okay, 1, 2, 3. And notice that for type A3, this green edges or green vectors, they all have the same length, square root of 2. But this one, blue edge, has length 1. So they have 2 different lengths. Okay, and then what about root system C3? For rank 2 case, B2 and C2, they are isomorphic. But C3, B3, they are not isomorphic. In this case, C3, the set of roots is still, we have A3 roots. We add something similar, but twice as long as them. Zero plus or minus 2. So I don't have that model right now, but you can imagine just make each blue edge twice longer. We have something like that. I don't have that stick, so I couldn't create this, but you can imagine. So it's bigger like that. So we have length square root of 2 for this and length 2 for this. And then actually not quite isomorphic. Oh, and by the way, both for the while group of P3 is really the same as the while group of C3. So while groups, we always have the same thing for Bn and Cn. Although as root system, they are not isomorphic, but their while groups are isomorphic. And these are the symmetry group of symmetries. Symmetries of the regular cube. So it has. Any question? Okay. You may wonder, what about the group of symmetries of other Platonic solids? So we have 2 more work. So what are the Platonic solids? We have tetrahedron, and a cube, an octahedron, and icosahedron, and dodecahedron, right? But in fact, these 2 symmetry group of this is really the same as the symmetry group of this because they are dual to each other. And these 2, they they are dual to each other. So we've seen that this is Weyl group of A3. Symmetry group of this is Weyl group of B3 or C3, the same. But what about this? It's not a Weyl group of anything. That's because that is something related to the fact that this kind of regular pentagon is not really inside any lattice. So we have crystallographic stuff, the axiom in our Weyl group or root system. So we don't have any root system in our definition whose Weyl group gives this symmetry group of this. But for these two, yeah, we do have. So in fact, there is a more general definition, which is more general than Weyl group. It's called a Coxeter group. But for Coxeter group, we do have the symmetry group of this. In fact, Coxeter, a special case of Coxeter group. But I'm not going to tell you more details about that. Okay, and then now let me tell you more about general situation. So the classical root systems. By the way, the irreducible root systems of rank 3 are these three things, like A3, B3, C3. And in general situation, root system type AN. And this is in fact the root system associated to this Lie algebra, like that. Here n is greater than or equal to 1. And what is this E? E is R to the n plus 1. And R is and delta is EI minus EI plus 1. Also, n. Because we are up to n plus 1. So the rank is n. So rank always is written as the subscript. But you may wonder, isn't the rank the dimension of E? So dimension of E is n plus 1, but the rank is n. What's the problem? So technically, I should have, this is not very accurate because I really have to cut this, quotient this by, I don't know, say L. L is the line, is the line spanned by this E1 plus dot 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 En plus 1. So we kind of, we don't use the whole space. We cut or quotient this by the line because everything here, their sum is 0. Their sum is 0, so we don't really use the space outside of this hyperplane who's consisting of vectors with component sum 0. But anyway, so the real dimension is n. And R plus, the set of positive roots of this form, Si, Ei, Ej, where here Ij can be anything different, but here J is less than, I is less than J. Why is this positive? Because in this case, Ei, Ej can be written as a positive sum of this, like Ei minus Ei plus 1 plus Ei plus 1 minus Ei plus 2 plus dot 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 Ej minus 1 minus Ej. So they are all positive. They are, each of them is a positive simple root, so it's a positive. And the Dynkin diagram we can easily draw. It's like that. So it's 1, 2, 3, we have n vertices, each corresponding to this root. So basically this corresponds to E1 minus E2, this corresponds to E2 minus E3, etc. This corresponds to En minus En plus 1. As you can see from this Dynkin diagram, we have just a single edge. That means the same length. They have the same length. These two roots, simple roots, they have the same length, and angle between them is 2 pi over 3. Okay? And this is root system type AN. And next, root system DN. And this is a root system of SO2 and C. And here n must be greater than or equal to 2. In here, E is really the R to the N, the whole space. R is plus or minus Ej plus or minus Ek, 1 less than J less than K less than is equal to Kn. And delta in this case, this is really, let me write this way, E2, it's like type A case, En minus 1 En, but we have one more vector like this. En minus 1 plus En. And in this case, R plus is Ej plus or minus Ek. Yeah, so in this section, I'm going to just show you, I'll just tell you these systems and without any proof, so just a statement. So in this case, the Dynkin diagram looks like this. So it's 1, 2, n minus 2, n minus 1, n. But of course, this corresponds to E1 minus E2. This corresponds to E2 minus E3. And this corresponds to n minus 2 minus En minus 1. And this corresponds to En minus 1 minus En minus 1 plus En, like that. Again, we have only single edge, so all the roots are of the same length, and adjacent root, they form an angle of 2 pi over 3. You may notice that I haven't shown you T3. Have I showed you T3 or T4? You know, whenever n is greater than 3, we cannot really visualize in three-dimensional space. But what about T3? Have I shown you T3? Yes, I showed you. Do you remember? This is T3 root system. T3. No? A3? But A3 is really the same as T3. If you can see that, what is T3? T3 Dynkin diagram is like that, right? This is T3, but you know, they are isomorphic. So T3 is the same as A3. So because of that, when we talk about Tn, usually we consider n greater than or equal to 4, because otherwise it's just A3 or other. Okay, what about B? Root system Bn. So this is the root system of the Lie algebra SO2n plus 1c. Again, E is the same. R plus or minus EJ plus or minus EK 1 J K N. So this is basically T. This is basically Tn, right? This is in fact Tn, but we add more vectors like this: EJ 1 JN. Delta, we can pick delta in this way. So it's like the delta in AN, or in n minus 1, union EN. We have one more. And R plus, in this case, exactly the same as this, except we only choose plus for EJ. I think it's not necessary to have this. It's the same as this, right? Because we have plus or minus, plus or minus. If you include that, you only have more vectors. That's not very efficient. Like that. So the thinking diagram looks like this. So 1, 2, dot, 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 n minus 1, n. But we have two edges with direction like that. So of course this corresponds to E1 minus E2, E2 minus E1. This corresponds to En minus 1 minus En. This corresponds to En. And notice that this, what is the length of each of these? Square root of 2. We use just a usual inner product. So square root of 2. So length of this is 1. Okay? So they have different length. And here the angle is 3 pi over 4. And so maybe you can see from this. This is B3. So in B3 case, B3 we have like that, right? So these two have length greater than this. Because this means this vector has length greater than the length of this. Okay? So we have two vectors of length square root of 2 and one vector of length 1. So here you can see these white dots. If you focus on these white dots. So we have two vectors of length square root of 2, one vector of length 1. And which one is, so we want to name them like a 1, 2, 3. So 1, 2, 3. How can you pick 1, 2, 3? This has to be 3, right? Because that's the only vector with length 1. What about this and this? Can we say anything like a 1, 2? Does it matter if I pick 1, 2, 3 or 1, 2, 3? Does it matter or not? It does matter because 2, so 1 and 3, they are not connected. That means the angle between 1 and 3 is 90 degrees. So 1 and 3 must be orthogonal. So which one is orthogonal to this with 1 and say x and y? X, y, which one is orthogonal to this? Can you see? X or y? X and y, you can see this is orthogonal, right? This is orthogonal, but this is not orthogonal. So this has to be 1. So 1 and 2 and 3. And what is the angle between 1 and 2? This means, what's the angle between 1 and 2? 2 pi over 3. Angle between 1 and 2, is that 2 pi over 3? Yes. Because these four vectors, they form a plane. They are on the plane. So we have, this is pi. This is pi over 3 and 2 pi over 3. So it's 2 pi over 3. And what about angle between 2 and 3? It has to be 3 pi over 4 So this was 4. And again, these 1, 2, 3, 4, 5, these vectors, they are on the plane. So this is pi over 4. So 1, 2, 3, so it's 3 pi over 4. So you can clearly see from this diagram. And again, 1 and 3, they form an angle pi. Oh yeah, we've already seen in one of the homework this week, whenever you pick two vectors, and then if you consider the span of them, they form a plane, and then if you look at those in the plane, you will see a root system of rank 2. So it's something like that. Okay, what about type C? I am being lazy and then write just on below this because they are really quite similar. So for type CN, this is going to be SP2N. SPN, we just write N. And what about this? This is the same. This is the same except we have 2 over here. Right? We have 2. So it's going to be 2 and 2 like that. It's the same except we change the direction like that. This is C3. And you can see B3 and C3, they are not isomorphic. They are thinking diagrams because we have to really consider the direction as well. So B3, C3, they are not isomorphic. Whereas B2, C2 is like this and this, but they are isomorphic because we only have 2 vertices. But for B3 and C3, they are different. Of course, here it's 2. All right. So these 4 root systems, AN, BN, CN, DN, they are called classical root systems. So let me summarize them. So AN, here n greater than or equal to 1. This corresponds to SL n plus 1C. So that it looks like this. And BN, here n is greater than or equal to 1. SO 2n plus 1. Like that. Dn is like this. And this corresponds to the root system of SO2n. And n is always the number of dots, number of vertices, because that's the rank. Here n must be greater than or equal to 2. N is greater than or equal to 1. This is almost the same as Bn, but the opposite direction, like that. And this SP and C. And notice that these A, B, C, they are defined for every integer n greater than or equal to 1. But we don't have to consider all of them because A1 is B1 is C1, right? A1, B1, C1, they're all just one dot. And B2, I told you already, is the same as B3, C2. What about D2? D is not defined for n equals 1, but D2 is only 2 vertices. So it's like this, without a third vertex. So it's really A1, direct sum A1. So it's D2 is not irreducible. But what about D3? I already mentioned this is A3. So corollary, SL n plus 1 C n greater than or equal to 1, SO 2n C n greater than or equal to 1, 3, SO 2n plus 1 C n greater than or equal to 1, SP n C n greater than or equal to 1. These all, they are all irreducible. Or simple, we say simple. Because an algebra, simple or semi-simple algebra, Lie algebra is simple if and only if its root system has connected Dynkin diagram. So they have connected Dynkin diagram, so they are simple. Now, finally, I can tell you the classification theorem for the semi-simple Lie algebra and also equivalently irreducible root systems. So, classification. Again, this will be stated without proofs. So, theorem. Every root system, irreducible root system, irreducible root system is one of them. Exactly. One of the following. Of course, up to isomorphism. AN, n greater than or equal to 1. Bn, n greater than or equal to 2. Cn, n greater than or equal to 3. Dn, n greater than or equal to 4, which is quite nice, 1, 2, 3, 4. Because we want to say exactly one of these. G2, we've already seen this. And now these are the things that I haven't mentioned. But I will only tell you this by drawing the Dynkin diagram. The fact is there is a root system with Dynkin diagram like this. But of course, construction of this is not quite simple, but let's just accept that. And E6, it looks like the Dynkin diagram is like this, and E7 like that, and E8. So the index or subscript always indicates the number of dots. So these four, they are called classical root systems. And these, they are called exceptional root systems. So we have complete classification of this. So what's nice about this classification is that suppose that you want to prove some property of a root system in general. Suppose that you want to show that a root system has property A, say, property P. Of course, you may prove this using just general theory, but you can prove this by each of these. You can prove type A case because we have explicit description of type AN with these roots. You prove this for type AN, BN, CN, DN. Okay, we prove them. And what about these exceptional root systems? It'll be very tedious, but they are. You can see it's a finite object, so it's only a finite root. You know explicit description of this, so you can just use computer to check whether this root system has the property. So this is quite common nowadays to prove some theorem about root system. Prove this, because these are not infinite object, we have to prove this by hand. But for this, just use the computer. And then that will be a proof of the statement for all general root system. But of course, people prefer a proof without doing all the case by case. But that is completely valid proof, case by case. Okay. And theorem. Now we can translate everything in terms of Lie, semi-simple Lie algebra. So the theorem is the root system. So let's say G is a semi-simple Lie algebra. And the root system of G is unique up to isomorphism, of course. So because, root system was defined using the Cartan subalgebra, so you have some choice for the Cartan subalgebra, but no matter what Cartan subalgebra you choose, you will always get the same root system up to isomorphism. And the root system of G is, so far in this chapter we define abstract root system, meaning the collection of non-zero vectors satisfying these four conditions. So root system of a semi-simple Lie algebra is indeed an abstract root system, meaning this is a root system defined in this chapter, chapter 8, right? Satisfying four axioms. So root system of a Lie algebra is indeed an abstract root system, and conversely, for any abstract root system, say R, there is a semi-simple Lie algebra with root system, whose root system is R. So it can be realized as a root system of a semi-simple Lie algebra. That means, therefore, the root system of a semi-simple Lie algebra is really the same as an abstract root system. They are really the same. So semi-simple, and also Lie algebra is determined by its root system. So semi-simple Lie algebra, there is a one-to-one correspondence root system. For abstract root system, they are really one-to-one correspondence. And if you want to look at simple Lie algebras, then we know that will be it corresponds to irreducible root systems. That means if you can classify irreducible root systems, we can classify semi-simple Lie algebras. But we know the classification theorem for this, so we can translate that into classification theorem of simple Lie algebra. Semi-simple is basically a direct sum of simples, so if you know simples, that's enough. So I'm going to finish by telling you this theorem. Finally, the theorem: every simple Lie algebra is isomorphic to exactly one of the following Lie algebras. So it's just type A, it is SLN, right? Where n greater than or equal to 1. And type B is SO 2n plus 1. So n greater than or equal to 2. SP for type C is this, n greater than or equal to 3. And for type D, it is 2n, n greater than or equal to 4. And then the exceptional Lie algebras, again denoted by the same symbols. So these Lie algebras, they are quite complicated, but still, this finite dimensional, we know exactly what these complete structure is known, so you can use computer to prove something. So if you again want to show some property of a simple Lie algebra, you can just prove each case by case. So these are called the classical Lie algebras, and these are exceptional. These are all possible simple Lie algebras. Okay, I will finish this lecture. Thank you for your